Hi friends, today we are going to learn about how to estimate a two-variable regression model by using LeastSquare method. In econometrics, we will come across different types of model. Among them, one of the best and one of the very easiest and classical model is a two-variable regression model. A two-variable regression model uh, is represented as yi is equal to beta 0 plus beta 1 xi plus ui. This is the classical linear regression model, population regression function of a two variable model, where yi represent the dependent variable, xi represent the independent variable, and ui represent the stochastic random error term. And least square is one of the method for estimating the two variable regression model. Mainly this model is known as classical linear regression model. Why least square is considered to be as the best method? Because it has so many optimal properties. Because the estimate that we obtain through the least square method has properties like linearity, unbiasedness, minimum variance, and based on comparing with the other estimate, it's said to be an efficient estimate. That is, it satisfies a theorem of Gauss-Markov theorem. That is a theorem highlight the properties of an estimated coefficient. That is why we call least square as one of the best method for estimating the two variable regression model. And this method is credited or attributed to Carl Friedrich Gauss. Carl Friedrich Gauss. He was a German mathematician, and mainly the theorem is also theorem of the optimal properties. Gauss-Markov theorem is also attributed to Carl Friedrich Gauss. And let us move on to the two variable population regression function. That we all know that this is an econometric model. Unlike a mathematical or a scientific model, this model incorporates a stochastic error term or a random variable ui, where ui and yi and xi are given and fixed variable, or they are non-stochastic in nature, but ui is a chance variable or a random variable. And why we are including a random variable into the relationship between these two variables yi and xi? Because unlike a scientific model, in social science we are mainly dealing with the qualitative or attributional variables like behavioral changes and so many fluctuating variables that we are dealing with in economics or in social science. Therefore, the relationship between the two variables like yi and xi are affected by so many unknown variables. That is, maybe some random phenomenon has some influence on this yi and xi that will adversely affect the true relation between yi and xi. That is why in economics many of the relationship between two or more variables are not exact in nature, or not that much accurate, just like what happened in science. Because in science, when two factors are related, we can connect that relation by stipulating or making all other influence of all other variables, just like humidity, then climate. These all variables we can control in a lab experiment, but in economics or in social science we are dealing with a real life phenomenon. That is many a time we cannot control the effect of such variables. Such variable create the adverse effect on the true relation between ya and xy. That is why in economic or in social science model we include this unknown or chance variable. Okay, let us move on to the importance of this two variable regression model. Therefore, yi and xi are the given and known fixed variables, and ui is a chance variable. Especially in regression or in real data, we can only estimate the known relationship. That is the relationship between yi and xi alone is estimated in a regression equation or in a real life data, or a given data explains only the systematic relation. This relation is known as systematic relation. Therefore, the change in ya can be explained with the known variable and also with the all other unknown variable. That ya is affected by the known and unknown variable, but in regression or in real data we get only the known variable. That relation is known as the systematic variation. That is the variation that xi creates upon y. And there is another variation, that is we call it as random variation. That variation is due to the unknown variable. For example, suppose we are studying about consumption and how income xi affects the consumer's consumption behavior, and there are so many other factors like age or gender or taste and preference or region, ethnicity and quality of the product, and so many other unknown factors are also influencing the consumption behavior. But that effect is not explained in the data, because we are only dealing with the two variables. That is, the first variable is the consumption and the another variable is the income variable, and that is we elicited through the our given data. Therefore, regression explains only the systematic relation, that is the relation between yi and xi. Therefore, in order to get a best estimate or a better estimation through the regression function, we assume so many, or we have so many assumptions related to ui, that we have to nullify or neutralize the effect of this ui upon yi. That is, the random variation should be the least, then only we will get the estimate of beta 0 and beta 1 as the best estimate, unless we will reduce the effect of the ui. Therefore, regression is one of the method of estimating the two variable regression model, and here we are applying this LeastSquare method is the one of the method through which we will minimize the effect of the random variable. Then let us move on to the relation, that is the regression explains only a conditional expectation of yi for a given value of xi. That means when we assign different values to the income based on income that a person behaves, or his consumption depends only on the income of the consumer, and all other factors, the effect of all other factors are neutralized by so many assumptions that I am not going into detail of all these assumptions, because we have so many assumptions that is related to this CLRM, that is classical linear regression model. That means we assume that this is a chance factor and it is not at all presented throughout the period, and its mean value is even though it is presented, the effect of that variable is somewhat equal to 0. That means mean value is equal to 0, and it is a non-autocorrelated or not creating any bias in the model, and so many assumptions, that's all the stochastic and other general assumptions are also we presented in the CLR model, and all these assumptions are only we assume all these assumptions because we have to say that the relation between yi and xi is so strong enough that will not never adversely affected by or not any other factors, that is ui. That means we will neutralizing the effect of ui with the help of all these assumptions of CLR. Then this model is a linear model because the relation between yi and xi is a linear straight line relation. By estimating this regression model, we will get a straight line. That a straight line is fitted with the help of this model. And there are different types of model, that is linear and non-linear type, but here we assume that the linearity is in econometrics. When we say about linearity is restricted to the parameter only, that is the parameter beta 0 and beta 1 should be linear. Then for example yi is equal to beta 0 plus e raised to minus beta I xi plus ua is not a linear model because here beta 1 arises as a power of the exponential function e raised to beta 1. Therefore, here we can say that beta 0 and beta 1 are not linear. Then yi is equal to beta 0 plus beta 1 xi square plus ui. This model is non-linear with respect to variable because here the variable xi has a power. But in econometrics, when we talk about linearity is only with respect to the parameter. The parameter should be linear and there is no such restriction upon the variable. That is suppose 1 by x or square root of x, that's all permissible under the linearity in econometrics. Therefore, in linearity in econometrics, we restrict the linearity upon the two coefficient beta 0 and beta 1. Okay, let us move on how to estimate this model with the help of LeastSquare method. For that we have to write the sample regression function, and I already said that through sample we can elicit only the information of the non-variable, that is beta 0 plus beta 1 xi, and sample information does not contain any information related to the random variable. Therefore, this is the sample regression function, and the regression is estimated on the sample data, and we will obtain the estimate of the beta 0 that is the that is the intercept term, and beta 1 is the slope coefficient. We have to find out the estimate of beta 0 and beta 1 by using the LeastSquare method, and this is the sample regression function, because I already said that the regression estimates only the relation that is known, or only the data they obtained through the sample can be estimated through the regression. Therefore, we will estimate the known relation between yi and xi. That is also a conditional expectation. That is for a given value of xi, how much is the estimated value of yi? That is we are going to obtain through the regression function. Then he already said that we are using LeastSquare method. That is a method by which we will reduce the effect of the random term in order to get the best result for beta 0 and beta 1. And we can write this estimate as beta 0 hat and beta 1 hat. These are the two estimates of the parameter beta 0 and beta 1. These are the two LeastSquare estimate of beta 0 and beta 1, and we can apply the LeastSquare method into this sample regression function. And I already said that YA, maybe if YA is equal to consumption, then XI is equal to income, then beta is nothing but the marginal propensity to consume, and beta 0 represent the autonomous consumption. And we can move on to the least square method. In least square method, it is an optimal, this method is very have some optimal property, because it will give you the best estimate by reducing the effect of all other factors. That is, we should estimate, or we will get an estimate that will represent the best fitted line into a sample data by minimizing or by assuming that the effect of all other variables should be the least. Then only we will get the best estimate from the sample data. That is the objective of the least square method. Therefore, in least square method, we will reduce or minimize the random variation, so that we will get a best estimate of the systematic variation of yi and xi. But let us explain the overall variation, that is total variation in yi, that is represented by sigma yi square, is equal to systematic variation, that is sigma yi hat square plus random variation sigma ui hat square. Therefore, in order to get the best estimate, we have to reduce this random variation. That is the objective of this least square method. That is, we have to minimize the error sum of square, or the least variation in the error variation or the random variation with respect to the estimated coefficient beta 0 and beta 1. Therefore, we have to minimize the random variation with respect to the estimated coefficient beta 0 and beta 1. Therefore, just like any maximization or minimization or the optimization problem of a function with respect to beta 0 and beta hat or any other given constant, then we can follow the constraint optimization, or here there is no constraint. Therefore, we can directly optimize the function with respect to the coefficient. Okay, let us write the function again, that is sigma ui hat square. We have to minimize the error sum of square with respect to beta 0 hat and beta 1 hat. Okay, let us write the error sum of square, that is nothing but sigma yi minus yi hat square. That is how this relation arises, how this random variation is equal to yi minus yi hat square. Then we already said that the total variation in yi is due to the systematic variation and the random variation. And in a regression line, the regression line only will give you the conditional expectation, that is the actual yi with the help of the given xi, what actually the estimate of yi, that is the yi hat. Therefore, in a regression line, we will estimate the yi hat or the estimate of the yi for a given value of xi. Then from this relation or the difference, that is there is an actual value and there is an estimate, and the difference between this actual and estimate is due to the presence of so many other variables. For example, we have income is equal to 100 rupees and consumption is estimated to be around 50 rupees. Estimated consumption is 50 rupee, but actually we derived a consumption only at 45 rupees. That is with a given income level of 100 rupees, 50 is the estimated consumption, but in reality the consumption incurred is only 45 rupees. Therefore, there is some difference in the estimate and the actual value. That is, we estimated 50, but actual consumption is only at 45 rupees. Therefore, other than income, there may be some factor that influence the actual consumption, because we estimated the consumption will be only 50 rupee, but he actually spent only at 45 rupees, maybe due to some other reason, that may be due to some supply shock, or maybe due to COVID season, or just like any other random factor. The situation does not permit him to spend 50 rupee. He only spend 45 rupees. Therefore, the difference between the actual and the estimate is due to some other random variable other than income. That is the explanation of the presence of random variable into our estimation. Therefore, the random variable or UI hat is obtained only through the difference between the actual and the estimate. Therefore, all the difference between the actual and the estimate is due to the presence of some random factor, and we have to minimize that random factor and its effect. That is, we are going to that we are doing in the LeastSquare method. Therefore, we expanded the equation, that is the random variation is nothing but the sum of square deviation of the actual dependent variable and the estimated value, and the difference between the actual and the estimate is the effect of the random variable. And we can write the equation as we already know that yi is equal to beta 0 plus beta 1 xi plus ui. That is the population regression function. And in a sample regression function, we have no information regarding the random error term. It only include the known yi and xi. Therefore, we will estimate the sample regression function only. We are estimating not the population regression function, but the sample regression function is going to estimate, and the sample estimate is written as yi hat is equal to beta 0 hat plus beta 1 hat xi, and this is the estimate of the sample regression function. Therefore, once again I will say that this is the population regression function, and this is the sample regression function, and this is the estimate of the sample regression function. And I already said that the random variable is obtained only through the difference between the actual and the estimate. And here we have the actual value, that is yi minus yi hat the whole square into sigma. That is the random factor. That is when we subtract equation 1, we will estimate the error sum of square by taking the subtraction between the equation 1 and 3. Then we will get the estimate of ui hat square is equal to sigma yi minus, instead of yi hat we can write the equation number 3 as beta 0 hat minus beta 1 hat xi. That this is a plus sign, but when we apply minus to the whole function, this two terms also become minus. Then this is the equation. Then we already said that we are optimizing a function subject to the two estimated coefficient beta 0 and beta 1 hat. Therefore, we have to minimize this function with respect to the beta 0 hat and beta 1. For that we will take the partial derivative of this function and set it equal to 0. Therefore, in order to minimize this function, we have with respect to beta 0 hat and beta 1 hat, we have to find out the partial derivative of this function with respect to beta 0 hat and beta 1, that is derivative of sigma yi minus beta 0 hat minus beta 1 hat xi the whole square with respect to beta 0 hat and set it equal to 0. At the same time, that we know that in optimization, in order to minimize a function, it has two condition, that is the first order derivative should be equal to 0 and the second order derivative should be alternative in sign based on the variable, and if it is two variable then it should be greater than 0, that is sigma yi minus beta 0 hat minus beta 1 hat xi the whole square with respect to beta 1 hat also should be equal to 0. These are the first order condition for minimizing the error sum of square. The next we can find out the derivative. How to find out the partial derivative of the function with respect to the two estimated coefficient. That the first one is that we have to find out that this here we apply the function of a function rule because it's a function raised to degree 2. Therefore, we will write first we find out the derivative of the entire function, then next differentiate the function with respect to beta 0 hat, then that equal to 2 sigma yi minus beta 0 hat minus beta 1 hat xi. This is the derivation of the entire function. The next we will derive the coefficient only, that is minus with respect to beta 0 hat we have to derivate it, then it is equal to minus 1 is equal to 0. This is the derivation of the first function, and similarly we have to find out the derivation of the second function yi minus beta 0 hat minus beta 1 hat. Up to this it is same. Again we have to find out the derivative of the beta 1 hat, then here there is minus xi is there, therefore minus xi equal to 0. These are the two derivative of the function with respect to the two estimated coefficient. The next here we can say that this 2 is a positive quantity and that is never be equal to 0. Therefore we can rewrite the equation as sigma yi minus beta 0 hat minus beta 1 hat xi into, that is minus is also not equal to 0. Therefore we can directly write the equation as equal to 0. The next sigma yi minus beta 0 hat minus beta 1 hat xi into xi. Again we can, here we can set an assumption that minus 2 that is not equal to 0 because 2 into minus 1 minus 2, from the first equation minus 2 is not equal to 0, so for we removed that term. Then again here 2 into minus, again minus 2 not equal to 0, that is also applied to the second equation and we remove the effect of that term also. And now we have two equation, then these two equation is generally called as normal equation. Then we can derive the normal equation, that is by assigning sigma, and by assigning sigma to the equation, that is equal to sigma yi minus here we have to look at it is a coefficient, it's a constant, therefore we are not by assigning sigma sign we have to multiply it with the total number of terms. Therefore we will apply because the sigma is assigned only to the variables and here it is not a variable, therefore we will assign n, that is number of terms. Instead of summing up it, we will multiply by the total count, therefore it's equal to n beta 0 hat minus, here there is a variable xi, therefore we will assign sigma beta 1 hat into sigma xi equal to 0. Then here first we have to multiply this function with xi, then assign sigma, that is yi into xi, then sigma, that is equal to sigma yi xi. Then next minus beta 0 hat into xi. Beta 0 hat again is a constant, therefore we will assign sigma only to the xi, sigma xi, minus beta 1 hat again a constant, we will assign yi xi equal to 0. Then again we can rewrite this equation by taking the minus sign into the other side, that is sigma yi equal to n beta 0 hat plus beta 1 hat sigma xi. The next sigma yi xi equal to beta 0 hat sigma xi plus, so here there is one mistake, that is sigma xi into xi, that is xi into xi, that is beta 1 hat sigma xi square. These are the two normal equation. Once again I will explain, that is first we will multiply each and every term with this xi, that is yi into xi, yi xi, beta 0 into xi, beta 0 into xi, xi into xi square, then assign sigma. Sigma here we will assign sigma to all the variable, and we have assign sigma to the constant, then we will multiply it with the n. And these are the two normal equation. The next we have to find out the value of beta 0 hat and beta 1 hat. For that we will convert this two normal equation into matrix form. Then in order to estimate this coefficient, we will convert the two equation into matrix form, that is sigma yi xi, that is in the right hand side. Then next that is equal to, we will convert them into matrix form by taking the two term outside, that is beta 0 hat and beta 1 hat, that will taken the other side. Then what is remaining there, beta 0 hat and beta 1 hat is gone to other side as two matrix. The next then remaining terms are n sigma xi, then next sigma xi the whole square. Then this is in the form that ax b, that is ax is equal to b, all are in matrix form, that is a is a matrix of coefficient, sorry, a is a matrix of variables. Then next x okay, this is in the form that ax is equal to b. Therefore we have to find out that ax is equal to b means beta 0 hat beta 1 hat into n into sigma xi the whole square is equal to sigma yi xi. Therefore in matrix we will apply Cramer's rule in order to estimate the coefficient of beta 0 hat and beta 1 hat, that is beta 0 hat is equal to, in matrix form we have Cramer's rule by replacing the first row by using the non-con, by the dependent side variable, that is sigma a1 divided by a, where a1 equal to, in order to estimate the first coefficient we will replace the first column by using this dependent part, that is sigma yi xi, then sigma xi divided by sigma xi square whole divided by the same matrix, that is n sigma xi the whole square. Then we can find the beta 0 hat is equal to sigma yi sigma xi square minus sigma xi sigma yi xi whole divided by n into sigma xi square minus sigma xi the whole square. Similarly, we can also estimate the beta 1 hat. For that, we will replace the second column, that is n sigma xi sigma yi xi whole divided by n into sigma xi the whole square. Beta 1 hat is equal to multiplying it n into sigma yi xi minus sigma yi sigma xi whole divided by n into sigma xi square minus sigma xi the whole square. And these are the two method or formula for finding the estimated coefficient of a two variable regression model.